Okay, while we were waiting between the segments, I drew out a little diagram here to illustrate the distribution of kinetic energies at different temperatures. The y-axis is just the number of particles with a certain kinetic energy, and kinetic energy is on the x-axis. And you'll notice that at lower temperatures, the curve is narrower, and it's also shifted to relatively low kinetic energies. So the average kinetic energy, which would be right about here at the peak, would be, say, right about there for the lower temperature. And for higher temperatures, the distribution is broader and also shifted towards higher kinetic energies. So the average kinetic energy at the higher temperature would be more like this kinetic energy right here. So you see, the average kinetic energy goes up when you raise the temperature, even though there will still be an overlap in the actual kinetic energies. And the reason that things evaporate faster when you raise the temperature is because if you look at the curves here, you have just a greater number of molecules that have enough energy to go off into the gas phase at higher temperatures. I've drawn a line here at some hypothetical value that represents the minimum amount of kinetic energy needed for a molecule to go off into the gas phase and basically be vaporized. And you notice the higher temperature curve comes in higher, and there's a much bigger area under the higher temperature curve from that point on up. And so there's a much larger number of molecules at the higher temperature that have enough energy to be vaporized, whereas at the lower temperature, there's a very small number of molecules that have enough energy to be vaporized. And so that's why the way to speed up vaporization is by raising the temperature, or one of the ways anyway. If the container is open to air, both processes occur. But the vaporization or evaporation tends to occur faster. And that's because once the molecules are vaporized, if the container is open to the air, the new gas molecules tend to leave the area, and they go up because gas molecules are in constant rapid motion in random directions. So once that water molecule becomes water vapor, it moves out of the area pretty quickly. And they're gone. And so there's nothing to condense back into a liquid. On the other hand, if the container is closed, then you reach an equilibrium. And what that means is that vaporization or evaporation will occur more quickly at first, but you eventually reach the saturation point. And that's basically the point where the air above the liquid is saturated with the vapor of the liquid. So when I say vapor, I mean the liquid that has recently turned into a gas. So in most cases, we'd be talking about water vapor. So eventually you reach a point where the air above the liquid holds as much of the vapor as possible. And that's the saturation point. Or 100% relative humidity. That's basically what humidity means, or relative humidity means anyway, is how much water vapor is there in the air compared to the maximum amount of water vapor that the air is capable of holding at the current temperature and pressure. And so if it's a closed container, you're eventually going to reach 100% relative humidity, which is the point at which the air is saturated with water vapor. And at that point, the rates of evaporation and condensation will be equal. And this is known as dynamic equilibrium. It's a situation where it appears that nothing is changing, even though individual molecules are changing. So if you have a closed container of water, you'll notice that over time, little beads of water will appear on the sides of the glass. And that's basically water vapor, which has evaporated from the surface of the water and has condensed on the sides of the container and are basically on their way towards sliding back down into the liquid. And if you look at it again and again and again over a period of time, as long as the glass or container remains sealed up, it appears that nothing is changing. But if you were able to look at individual water molecules, you would notice that at any given moment, there are some that are evaporating and others that are condensing. And that in fact, at any given moment, the number of water molecules that are evaporating will be the same as the number that are condensing. And so the overall, basically overall, nothing changes, but individual molecules are moving back and forth. And so that's a dynamic equilibrium. This was kind of an aside here. So going back to the open container, so if the temperature is increased on the open container, or in other words, thermal energy is added, then what happens is the energy distribution shifts upward. Like I was showing in that little diagram I drew here. If you raise the temperature, the energy distribution shifts upward and it also broadens. And the end result is that a larger percentage or a larger number of the molecules will have enough kinetic energy to escape the surface into the gas phase. And the vaporization rate will increase as a result of that. Okay, so raising the temperature is a way to increase the vaporization rate. If the surface area is increased, that's another way to increase the rate of vaporization. So think of water that's spilled on a floor. Which way would it evaporate faster? If it's sitting in a glass or if it's spilled on the floor and spreads out all over? It evaporates more quickly if it's spread out. And that's because evaporation occurs from the surface, and the greater the surface area, the greater the number of molecules that are able to evaporate because they're at the surface. This is actually one place where the difference between evaporation and vaporization is significant, in that evaporation can only occur from the surface of a liquid, whereas vaporization can occur not only from the surface, but within the body of a liquid. So, but for evaporation anyway, if you have more molecules at the surface, the evaporation rate will increase. Also, if the intermolecular forces are weaker, so for example, if you're talking about alcohol instead of water, that requires less kinetic energy to escape the surface at a given temperature. Okay, so you require less kinetic energy to escape the surface, and therefore a larger percentage of the molecules will have that much kinetic energy. And that means that the evaporation rate increases. And these are known as volatile liquids. Volatile liquids just means relatively low boiling point. They evaporate quickly. And so these would be things like, say, gasoline, acetone, and say alcohols, or at least the smaller molecules in the alcohol family. Non-volatile liquids, as an aside, would be the opposite. High boiling points, and they evaporate slowly. And examples of those would be things like motor oil, or other types of oils like olive oil and corn oil and things like that, and so on. Water is sort of in between volatile and non-volatile. So water is considered to be sort of moderate volatility. Okay, so looking at the energy changes during vaporization, if water were in a thermally insulated container, thermally insulated meaning no heat in or out, meaning no heat in or out of the container. There could still be heat going in or out of the water, but the container essentially becomes the universe as far as thermodynamics are concerned. So there's not going to be any heat entering or leaving the container. So let's see, if water's in a thermally insulated container, what that means is the temperature of the molecules left behind will decrease as evaporation proceeds. And that makes sense when you think about it, because the molecules that evaporate are the highest energy molecules. They're the ones with the greatest kinetic energy, and temperature is a measurement of the average kinetic energy of molecules. So the segment of the molecules that are evaporating are the ones with the highest kinetic energy. And the average kinetic energy of those molecules that are evaporating will be greater than the average kinetic energy of the molecules that are left behind. So in other words, basically the hottest molecules are evaporating, leaving the cooler molecules behind. So the temperatures of the molecules left behind will be lower than that of the molecules that evaporated. And that's just another way of saying that vaporization or evaporation are endothermic processes. So let's see, the molecules that leave, molecules that leave take relatively large amounts of energy with them. They take that energy away with them, and that means that the average kinetic energy of the molecules left will be less. And since, again, average kinetic energy is another way of saying temperature, that means the temperature of the molecules left will be lower. And the conclusion here is that evaporation and vaporization are endothermic. And that's easy to remember because endothermic means you have to put energy in to get it to happen. And, vaporization is boiling. You have to put energy in water to boil it. No kidding, right? So that should be pretty easy to remember. And the human body uses this fact a lot for, especially at this time of the year, for cooling. When we sweat, the water passes through our pores onto the surface of our skin, and hopefully there will be a nice breeze to come along and help that water evaporate from our skin. if and when the water eventually does evaporate, it takes quite a bit of energy with it. In other words, quite a bit of heat. And so having sweat evaporate from your skin is actually a pretty efficient way to cool yourself down. Unfortunately, Buffalo summers tend to be pretty humid, and there's not always a nice breeze to help the water evaporate from your skin. So having sweat on your skin that doesn't evaporate can be pretty miserable. But when it does evaporate, it is very cooling. And that is actually one reason why people say things like, oh, it's a dry heat. It's because when the humidity of the surrounding air is low, the air is easily able to accommodate more moisture in it, and your sweat will evaporate more quickly in places like Arizona than it will here in Buffalo. And so it's true that 100 degrees in Arizona feels quite a bit cooler than 100 degrees here in Buffalo would. And that's just because your sweat is evaporating so much faster. In fact, people from places like this who move out there will often tell each other, be extra sure if you're going to someplace like, say, Arizona, to keep hydrated, because your sweat out there evaporates so much faster than it does here that you often don't even realize how much liquid you're losing. And so you have to be careful to keep drinking, even though it doesn't feel like you're sweating very much. Okay, so condensation is the opposite of evaporation. Or the opposite of vaporization, if you prefer to look at it that way. And that means that condensation is exothermic. Heat is released when water condenses. And a good example of that is a steam burn. If you sort of stick your hand above a boiling pot of water, and by the way, I'm not recommending that you actually do that, you will actually get burned. And that's by the steam, the water vapor condensing on your skin releases an enormous amount of energy when it does that. And it's condensing on your skin, so the energy goes into your skin and it burns you. And so that is an exothermic process. So let's see. Also, for vaporization, any given substance will require a certain amount of energy to vaporize it. And that amount of energy, it varies basically according to what the substance is. So the amount of energy it takes to vaporize a given amount of a substance actually goes along with the substance. And in fact, you can even identify a substance based on how much energy it takes to vaporize a certain amount of it. And that amount is known as the enthalpy or heat of vaporization. Okay, that's a pretty important concept. The book really seems to like calling it the heat of vaporization, but the formal term is enthalpy. So just in case you hear that, it's really the same thing. And it's the amount of energy that's required to vaporize a specified amount of a substance. And that would normally be at its normal boiling point. And 1 atmosphere of pressure. because changing the pressure can, allow you to vaporize something even at room temperature, and that would involve a different amount of energy. The symbol for this quantity is delta H with a little VAP after it for vaporization. And the specified amount is usually either 1 gram or 1 mole. I'm underlining 1 mole because that's the amount that the book seems to favor. Technically, enthalpy of vaporization would refer to 1 gram of the substance, and molar enthalpy of vaporization would refer to 1 mole, but not to get too technical about it. And a good example of that would be, for instance, if you boil water. H2O liquid going to H2O gas is vaporization. The enthalpy change for that process would be the enthalpy of vaporization for water. And that's 40.7 kilojoules per mole of water. So you have to put 40.7 kilojoules of energy in for every mole of water, or in other words, for every 18 grams of water that you want to vaporize. Okay. The enthalpy of vaporization, or heat of vaporization. I want to keep saying enthalpy of vaporization because basically every textbook I've used until this one insists on calling it enthalpy of vaporization. And sometimes people call it heat of vaporization, but it's kind of treated as a slang term. So anyway, the heat of vaporization is always positive. And that's because the process is endothermic. But there are different values for different substances. And also, it depends on temperature, albeit weakly. Which is why it's specified that it's usually measured at the normal boiling point of the substance. It's actually usually, the number's usually a little bit lower at the normal boiling point than it is at other temperatures. And condensation which is the opposite of vaporization, would go H2O gas to H2O liquid. And the delta H for this process, which I'm going to call the heat of condensation, would be the same number, but with the opposite sign. Oops. So that would be negative 40 kilojoules per mole, because this process would be giving off that much energy per mole. Heat of vaporization can also be used as a conversion factor between an energy change in a chemical reaction and the amount of substance that is reacting. Okay, so the amount of substance, actually it could be either the amount of substance reacting or the amount of substance produced, and the overall energy change. So an example of that could be, for instance, calculate the amount of energy in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. Well, what we have here, we know that the heat of vaporization of water is 40.7 kilojoules per mole of water. So what we're going to need is to find out how many moles of water we have. And we have 2.58 kilograms of water, but the masses in the periodic table are all given in grams. So we're first going to have to change that kilograms to grams. And so 2.58 kilograms is 2,580 grams, or in other words, 2.58 times 1,000. And then once we have the number of grams, we can look at the periodic table and add up the fact that there's 1 mole of water for every 18 grams of water. So kilograms cancel with kilograms, grams cancel with grams, and we have moles of water as our answer here. And this is 143.3 moles of water. That's a lot of moles of water, but 2.58 kilograms is a lot of water. And so if we know how many moles of water we've got, and we know how many kilojoules are required for each mole, then all we have to do is say Q, which is the abbreviation that's usually used for an amount of heat, would be the heat of vaporization (40.7 kilojoules per mole of water) times 143.3 moles of water. Moles of water cancel out, and we get 58.34, and that will be in, oops, sorry, not joules, kilojoules. For significant figures, 2.58 was only 3 significant figures, and the heat of vaporization was only 3 significant figures. So 5834 should be rounded off to 5830 with no decimal point. So 5830 kilojoules. And so this is how you can use heat of vaporization as a conversion factor. Okay, we've got, we're up against 34 minutes now, I guess. So I'll stop here and go on to the next segment in just a moment.